Hello, it's James from XRobots.co.uk. This is part 10 of Robot X, the reconfigurable sci-fi robot. This is a real robot that walks along. We've done quite a bit of walking development. At the moment I'm actually attaching the arms though, and last time we made some upper arms, and the forearms are going to be whatever character we dress it up as. So we've already dressed it up as Bender from Futurama. This is the last proper episode on Robot X itself, although we might return to it on its own in the future, and next time we're going to be building another character on it, and I'm going to tell you what that is at the end of the video. We need to build a control system for the arms, but I need to change some of the motors and things I wasn't very happy with last time, mainly because of the arm wobble we've got here, and it's actually down to this backlash in this gear, because the gear is actually loose on the motor. Also, this bevel gear isn't very good, it tends to pop out, and that's partly because of the flexibility in the bit of studding I put in there, and partly because of flexibility in the motor. So I'm going to change this gear assembly to something a bit more solid. And that looks like this. So there's going to be a big spur gear in place of that bevel gear, and the side plates of the robot here are now one continuous plate. So instead of having the motor attached to the front part, it's actually all one plate, so the motor will be braced much better. Also, it's going to be a motor with a 90-degree worm gear in it, so I can actually press the spur gears together and make a good contact without having that 90-degree angle and the two different bits of flex. And here's my 3D printed part, which replaces the existing hub and gear. So this is all printed in one piece, so we can still screw those other bits to the other side. And we've got a bearing in here with a little collar on that fits a steel tube. So we've got 12mm steel tube now to actually hinge the arms on instead of the 8mm studding, so it's not so bendy. And we've got these little plastic collars, they fit in the bearing to make a nice tight fit on both of them. This is one of the motors. This is from Gimson Robotics, which is where I got the actuators for Robot X's legs. And it's quite a substantial worm gear gearbox with that right angle shaft on. The other one here I've already mounted on a 3D printed bracket with the spur gear, so that should mesh nicely like so. So let's take the other bits and pieces off and see how that fits. I've got captive nuts and grub screws to hold this steel shaft in, so we can do that up and it will hold it nice and tight to stop it rotating, and that's so I can use it as a reference to measure the rotation of the arm. Right, we need to unscrew the arm from that and screw it back onto here now. I've put a stopper on the end of that tube to stop the arm falling off. There's a nut and bolt underneath that's pinching it and holding it on. It's also got a grub screw so I can stick the pot shaft in there for measuring its position. So both arms are on, but we need to attach the motors. Now I don't have symmetrical motors, they're actually both right-hand ones, so they need to be mounted on opposite sides, but the shafts aren't in the same place, so they need to be mounted at slightly different angles, but they fit nicely back there, so it shouldn't have too much impact. That seems to be working pretty well. Of course the arms in reality won't ever do a 360, they'll probably do about a 270 because the pot won't turn round for feedback any further than that, but the motors seem absolutely great. So there is a bit of backlash in that motor, but it's actually very, very tiny and pretty much what you'd expect from a good quality gearbox. Now with that steel tube in there as well, the arms are much less wobbly, so that's going to be much more solid. I've got two motor drivers for those two DC motors. These are the IBT4 motor driver, not the BTS 7960 that I used for the legs. These can handle about 20 amps I think, which is more than enough, and I've got plenty of space in the arm to fit them, so now I need to wire that up and we can get some motion. The servos of course have got their motor drivers built in and their feedback pots, so they don't need any motor drivers, we can wire them in, but they do need some power regulators, so I've got these turning gear battery eliminator circuits, which are for RC, which will regulate the 12-volt batteries down to about 5 or 6 volts, which is what the servos want. I've wired up some stuff to the motor drivers, mainly power here, and also one wire to go to the other motor. And we've got some signal wires here, which are basically a ground wire and the PWM, which is one PWM wire for each direction of each motor. So now we just need to fit a Arduino Pro Mini in here, which is going to act as an I2C slave device to the main Arduino in the robot, and we can then get those arms moving. Well, it looks a bit fuller in there now. I've fitted the Arduino Pro Mini, and now we can do some coding and do some testing and hopefully get some motion out of it. I've written some Arduino code for each of those Pro Minis to control the servo positions and to control the positions of the motors. So we're using the servo library for the servos and the Arduino PID library for the motor positions. Some people call it PID. We've got some variables declared here which are for the demand positions of those joints, and we've also got two variables for the potentiometers we're reading in to measure those joints. Now everything's running on multitasking here, so we're not using delay in the loop, so we've got some variables declared there for the timing, and then we've got our PID controllers being set up here and our servos being declared. Now I'm using serial for now to go and send data to those. Eventually it'll be I2C, which we'll come on to in a moment, so the serial port is getting declared, and we've got some pins here, so these are the PWM pins which are going to drive the motors, and these are the pots. We've attached our servos and sent them to the mid position, and this is in setup, which runs before anything else. We've also done the PID setup, which is straight out of the library example. Here's the timer that sets off the loop when it starts, so this means that this loop within the main loop will run every 10 milliseconds, which is 100 times a second. I'm doing a counter here, which is later written on out to the terminal, so I can see that it's definitely running. So we're reading our analog pots. I'm using serial, as I say, so this is basically sending those pot values straight back to the console as well as the count value. For now I'm reading the values from serial, so I'm literally typing them in on the terminal to send the joints to different positions, and that's what this is. So this is reading those demand positions we mentioned. It then looks for the new line character, echoes them back to the terminal, and does some stuff here constraining them. This is to stop the joints moving too far so the motors don't burn out when they hit their end stops. It's also writing out the servo positions, and that will send those servos to the positions that have been read from the serial terminal. Down here I've offset my pot positions by taking away 512. They're 10-bit, which means they go from 0 to 1023, so this makes them centre around 0. The set point for that PID controller is the actual rotation that I give it on the serial terminal, and it then does the PID compute. And basically it drives the motor in one direction if the value is smaller than 0, and it drives it the other direction if it's greater than 0. If it's in the middle at 0, then it stops the motor, and it does that for the other motor as well. So I've currently got the joint positions being echoed back to the terminal here and nothing else. So the first one is the main rotation, the next one is the lift out, then we've got the two servo positions. So if I was to modify the main rotation only and just send in the data for the others the same as they are, we should see that rotation. And if I bring the lift out, so that's the main lift out, and if I were to modify the other two there, then we can see those move quite nicely. Let's go the other way on those. That seems to work pretty well, so let's just put that back now. So that seems pretty good. The next thing to do is make those arms controllable from the main Arduino that controls the robot, so we can write everything into the main program loop. This is an Arduino Duo, which is 32-bit and 84 MHz, so it's fairly substantial, and the plan was going to be making those arms I2C slave devices, and that's because there's no serial ports left, because I've used them all for the inertial measurement units. However, I'm actually only using the RX pins. I'm only receiving data from the inertial measurement units, so I can actually use the transmit pins on those serial ports to send data to the arms. So for now, I'm going to make the arms actually serial devices, and I'm going to make the new remote control an I2C slave device. It's probably pretty hard to see what's going on in here now, but essentially I've got some level matchers because the Arduino Duo is 3.3 volts and the other Arduinos are 5 volts, so I've got that serial TX pin going through the level matcher and off to the arms. So that goes up to this wire and it combines with the wire here that comes with the power. So I'm using a USB power bank to power the electronics. So I've got another plug here since it's got two sockets. That one powers the Arduino Pro Minis in the arms, so I can disconnect them if I want to. And then the serial line gets combined into these wires that go off to each side. To send and receive the data, I'm using Bill Porter's Easy Transfer library, which zips it up into binary, puts a checksum and a header onto it. You know exactly what data you're expecting at the other end, so if the checksum is wrong or the data length is wrong, then it chucks it away and you don't end up with corrupted data in the wrong place. So that's much better than doing parse ints, unless you're going to write your own kind of error checking around it. So all you have to do to use this library is include the library, set up your data structure, which is the same at both ends, and then basically you attach it to a serial port, and all you have to do to send the data is do et.senddata, or whatever you've called your data structure. On the receiving end, it's set up very similarly, so you've got the same data structure there, and you can test to see if there's any data being received, and then receive it, and all you have to do is refer to it as mydata.variable name, or whatever you set up in the top. So here it's called mydata. In mine it's going to be called mydata_arms. So in my Robot X code I've set up my data structure here. So I've got both the left and right variables being sent in one data structure because they're sharing a serial port. Now I want to make sure that my sending Arduino is running more slowly than the receiving one, but in fact the robot's running at 100 Hz and so are the Pro Minis on the arms. So I've got another little multitasking statement here which checks the time arm interval, and in fact that part is set to 20 milliseconds. So this part of the code only runs at 50 times a second, which means it's half the speed of the receiving end. So if the time is elapsed, then basically it does et1 send data, because my data structure is called et1 in this case. On my left arm, I've set up the data structure to use both the left and right variables, so it receives all of them, but then of course it's the left arm, so when it comes to actually using the variables, it ignores the right ones and just strips the left ones out. And in my right arm, again, it receives all of the variables, and then it just takes the right data. And of course that means I can share a serial port with both of those, and they just ignore the data that's not for them. So now, despite some dodgy power wiring we need to tidy up, we do have the arms synced with the legs. So as it leans one way, I can make the arms move one way, and those are all driven from the same program loop. I originally designed the remote to look like a candy cane because I really like Christmas, but it's only got space for 7 buttons, and that's a bit of a rubbish reason to design a remote that size. So basically we're going to make a new remote that's got some analog controls on, a little display, and many more buttons and menu options. And that's going to enable us to send and receive data from the robot, but now we really have run out of serial ports, at least those with an RX pin spare, so we are going to have to make an Arduino that sits here, which is an I2C slave device, and that talks over Bluetooth to the transmitter and receiver. Here's the design for my remote control. Normally I build 2 parallel plates with spacers and you can see inside it, but I've decided to box it in this time and print an actual box. We're going to put an Arduino Mega in the back, and that's going to allow for multiple serial interfaces, so we can have one that talks to the robot over Bluetooth, and then we can plug into the USB port, and we can plug that into a laptop or a tablet and get some more visual data plotted. So the top panel is going to have some things fitted I mentioned last time, including a joystick with 3 axes and a display in those holes, and then we've got this panel here with lots of buttons and switches there. So essentially it's in 2 panels that screw onto the bottom, so I could reconfigure either of them in the future without reprinting all of it. Alright, here are the parts. So I actually ran out of grey filament halfway through that, and I had to swap the filaments, so now it's got this lovely 2-tone look about it. I've got the 2 panels that fit on there, which are both printed in ABS. The bottom is actually PLA, so it didn't warp, and I think that's going to look pretty good. So that's obviously my display that's going to be fitted in there. I've got all the mounting holes in there, and that's my joystick that's going to fit in there. There's space for the Arduino Mega right in the back there, and we've got a number of switches and things to fit. So here it is with all the buttons and things fitted. So we've got that lovely joystick that moves in 2 axes, and the top turns as well, so we get 3 axes out of it. This could be the remote to kill all remotes, so of course it could be programmed to control a number of different robots as long as they don't need more than 3 analog controls. Now I just need to wire all the buttons in, of course, and actually make it do something. Right, we're mostly wired in. All my switches, of course, are wired to digital ins on the Arduino, of which there's lots. The display is I2C, so that's fine as well. I've got 2 more buttons to scroll up and down with, which are wired to digital inputs. And the joystick, its Hall effect sensors work just like pots, so those are wired to some analog ins. Right, it's all powered up. I don't know if you can see the blue flashing light on the remote, and on the display it says Robot Remote XRobots, waiting to pair to Bluetooth. And if I turn the robot on, should hopefully find that when Bluetooth pairs, the light comes on, and now it says paired to robot. So I've just set up a really simple sketch for now that uses the I2C library and the liquid crystal library. It declares all the buttons as integers and various things. basically does the little display thing there on setup, sets up the serial port, which is actually the one to the console, which could be plugged into a laptop or something else cleverer. And basically at the moment I'm just reading all of those things in and sticking them straight out to the serial terminal. So if I switch these switches, we should be able to see all those ones and zeros changing. And if I move this around, we can see the numbers on the end changing, which are the analog values. So the pairing sequence is pretty easy actually. That's just a thing here which basically says waiting to pair, checks the state of the Bluetooth connection, flashes the light, and basically waits a second before it sends data when it sees that it is paired. And then in my main loop, it checks that pin again, says to run that sequence if basically it isn't paired, and if it is paired it just says it's paired, and that seems to work pretty well. So these buttons eventually will be for scrolling through different menu options. Obviously these buttons can act like shift keys, so we could make use these as binary buttons and make all of these buttons do something else, or we could scroll through this many times and change the function of the whole remote for different things. So we could have the joystick for walking, or it could be for moving the head, or it could be for moving the arms, or different coordinated moves, or these could replay moves, sounds, whatever we want, and we can keep scrolling through and have multiple menus and sub-menus. So how are we going to get the data from this remote onto the robot? So what we had before with the old remote was, well, we got the Arduino Duo there, and piggybacked on the back of it was a little Arduino Pro Mini. And that's actually connected with something like 7 digital pins straight into the Arduino Duo. And then we had our Bluetooth serial interface here connected to the remote, and that was connected to the little Pro Mini. And it read the serial data, and then it basically pushed digital pins as if the buttons were connected directly to it. And we could read these buttons in. But now we've got far more buttons. We've got the menu option, but we've also got 3 analog controls as well that we need to read in. So how are we going to do that? So what we're actually going to do is keep the Pro Mini, and we're going to take the serial data from this remote, and then instead of using digital pins, we're going to use I2C. So we're actually going to take another link from this Pro Mini onto the Arduino Duo's spare I2C interface. Now ideally we just go from the serial Bluetooth straight into the Duo, but there aren't enough serial interfaces on, at least for receiving, as I already said. We do have some for transmitting, so when we send data back from the remote, we can send that straight out of the Duo, back over that way. Now Bill Porter's helpfully done another easy transfer library for I2C, so we just have to build this staging Arduino to stage the data from serial through the Bluetooth connection to I2C. Now you can get I2C serial ports to add more serial ports to the thing, but basically they're more expensive than the Pro Mini that's already sat there. So I'm not going to go into the code too much, but as you'd imagine, the Pro Mini has another version of easy transfer running on for I2C, takes the data from the Bluetooth serial port from here, and basically goes and sends it on, and the Duo runs code to receive it. And that's how it works, so that gives me that extra serial port. Now the remote is set up pretty much as a dumb terminal, so the key presses just get sent to the robot, the modes up and down get sent to the robot, and the robot actually runs the master controller and returns data for the controller to display on its remote there. And that means the controller doesn't lose sync with what mode it's in with the robot, because the robot is literally changing mode and telling the controller what mode it's in. So if we power on the robot, we should find that Bluetooth pairs, and it should show us some data. And we can see in the bottom left here, we've got a counter which is actually running on the robot to show us the program loop is running, and 2 zeros, and these are inertial measurement units. So if I pull the robot around, we should see those values changing. There we go, and they look like they're centering around 0 or so on. I haven't got the decimal points because I don't really need them. I just need to check they're centering around 0, and everything looks good. I've got various modes defined on the handset here, so if I scroll through, it goes up 1, 2, and I've got different descriptions here I've just put in. And these are actually just sending the button presses to the robot. The robot is controlling what mode it's in and sending that back to here. And that means the handset there never loses sync with the robot as to which mode it's in. So if we now go and put the some power on the arms there, and we scroll into arm demo, it should put its arms up, and now the controller stick here is mapped. So if I move this around, this way moves the arms this way, up and down rotates them, and turning it rotates the elbows. So we've got quite a range of motion there. And if we scroll back out of arm demo mode, it should put his arms down. And of course we could map any of these buttons to do something different. So we could have preset positions for the arms, the controller could be mapped to anything, the switches could do something, we could have an infinite number of modes that we can scroll through. So perhaps all these controls completely change, and of course that would just be a different block of code on the robot. So we could map either arm, the head, combinations of motions with some manual control, or whatever we need for the characters that we build. So I'm quite happy with that as the new controller. As I say, it could be used for lots of different robots, and it's also got that USB port and other serial interfaces on the Arduino Mega, so I could put another Bluetooth interface from this to somewhere else, or plug this into a computer or a tablet or a smartphone, have another display, or we could interface it to the virtual world like we've done with Ultron's brain. But now it's time to announce what the next character is going to be that we're going to build on the robot. Obviously you can see it's a lot more robotic now than Bender was with its arms. If you imagine a head assembly being on there as well, styled for the character, as well as the forearms and hands, and perhaps complete covers. So I was going to do an Iron Man suit that walks along by itself, perhaps an Iron Legion robot. Obviously it would have to be quite stylised, a bit like the Igor suit. But I think I've done enough Iron Man projects in my channel now. Some people suggested another Ultron that walks along, but again we've done a year plus of the Ultron project, so check that out. So I heard there was a new film coming out, and it's Spider-Man, so we're going to do an Iron Spider-Man. Obviously it is going to be stylised and quite robotic and quite armoured, not really like what's in the comics. It's going to pretty much be my own inspired design, somewhere a cross between Iron Man and Spider-Man, with Spider-Man inspired gadgets. So don't forget to check back next time for more updates on that, and subscribe for all the other projects in my channel. Now most of my projects are funded by Patreon, so have a look at patreon.com/XRobots and you can get access to some exclusive rewards, including a live broadcast with me and all my videos early. Also don't forget to check out my Instagram feed for some sneak peeks and other pictures. Alright, that's all for now.